Gerry O'Sullivan, and the last speaker is Gerry O'Sullivan, and he's going to talk about spectroscopy for identification of plasma sources for lithography and water window imaging.
Okay, well, before I start, I'd just like to thank the organisers for giving me the possibility to present our work, which you can see is a collaboration with a number of Japanese groups. The main player in this is Takashi Yashiguchi at Tsunomiya University, and also a lot of support from Chihiro Suzuki at NIFS, with theoretical support from Bowen Lee and Lanzhou. Okay, so just a quick overview of my talk. It'll be a little bit about some basics on laser-produced plasmas, because contrary to the talks we've had up to now, which have been dealing with femto-nanosecond pulses and nanoplasmas, we're dealing with picosecond and nanosecond pulses and considerably larger plasmas, and some technology as well, a little bit about lithography and water window applications. And in all of this, I'll really be dealing with unresolved transition arrays. So, just to go on, to start with, this is the laser-produced plasma. So the laser comes in from the top onto a solid target. One produces a plasma by multiphoton ionization, and rapidly you build up to a density which is determined by the laser wavelength, and the bulk of the laser radiation is absorbed in the critical density layer here, which is determined by the laser radiation wavelength. Sorry. The temperature you get to is determined by the power density, as well as the wavelength. And then the average ionization stage that you end up with is determined by the atomic number of the target and the electron temperature. So basically, the higher the power density, the higher the temperature and the higher the ion stage. And because the densities can be very large, opacity can be a major issue. So if you're trying to build a source, the big challenge usually is radiation transport, and I'll come back to that in a moment. So what does a typical spectrum look like? Well, this is a spectrum actually of cerium oxide containing about 1% cerium by number, and it contains some lines, recombination radiation, Bremsstrahlung, and also one gets this unresolved transition array, which is basically an array of many thousands of emission lines lying very, very close together. And these can be extremely bright. In fact, they can be by far the brightest features in the spectrum of a laser-produced plasma. Now, the theory of these things has been developed a long time ago, largely by Jacques Bosch, Claire Bochernot, and Marcel Clapich, who basically developed a model to parameterize these unresolved transition arrays in terms of various moments of the arrays. And the moments are defined in terms of basically the energy difference between the two states involved, multiplied by a line strength factor. So they're essentially intensity-weighted distributions. And from an experimental point of view, which is the factor that's most interesting, in fact, is the shift of the if you like, the position of this intensity, peak intensity of the array from the difference between the energy, or the difference between the centers of gravities of the two arrays concerned. And that difference is determined by effectively the population. If you're looking at these kind of transitions here, and the strongest arrays we're going to deal with are things like 4D to 4F. So this is the N here is the occupancy of the 4D shell. So as the occupancy decreases, this term here decreases. So you expect that the array will shift towards lower energy or longer wavelength, but it's also determined by the product by a summation over Slater-Condon factors, which typically move to higher energy. This goes to higher energy as the degree of ionization increases. So there's an interplay between both of these terms, and for low atomic number materials like tin and so on, if the Slater-Condon factors dominate, so the array moves to shorter wavelength with increasing energy, whereas when you go to very high Z materials like platinum or bismuth or whatever, this term here dominates, and the array shifts to lower energy with increasing ionization. Now, what do these things look like? Here's an example of an array in tin, and you can see that the transitions tend to pile up on top of one another. This is a 4D to 4 to 4 array, delta n equals 0. And the other type you can have is where delta n is equal to 1, and in that case, the transitions move to shorter wavelength with increasing ionization. This is basically the spectrum of zirconium. These are 4p to 4d, and sorry, 3d to 4p and 3d to 4f transitions. A factor that has been well known for these arrays for a long time is that if you look at 4D to 4f excitation, you also have to consider subvalence 4p to 4d, because in that case the energy separations are approximately the same. You get strong configuration interaction, which leads basically to a spectral narrowing, and the array gets you get a very intense ray in a very narrow energy region. And also this configuration interaction assists, if you like, in the piling up of the arrays from different ion stages. Now, why would anyone be interested in these at all? Well, the main reason comes from interest in lithography. Some of you may know that we're about to, well, the semiconductor industry is about to move towards an operating wavelength of 13.5 nanometers, simply because mirrors are available at that wavelength, and the mirrors would have a reflectivity of around 70% in a bandwidth of around 4%, but when you cascade a number of mirrors, as you have to correct for aberrations and so on, you get a very small 2% bandwidth. So if you've heard of the 2% band of 30.5, that's because you need 11 reflections in a tool to basically get a good image from the mask here onto the resist. To date, the source powers obtained have been in the order of 90 watts, obtained by ASML in the Netherlands and also by Gigaphoton in Japan, and the aim is to push this up to about 200 watts. In terms of how these scale with Z, okay, for the source at 13.5 nanometers turns out to be a UTA in tin, the 4-to-4 UTA in tin. There's also a suggestion to use similar UTA in gadolinium, and we're interested in using the same UTA, if you like, in the water window. Well, there are a number of problems. The main problem is that as you go up in atomic number, you have to go up to higher and higher charge states to get these UTAs, which means that you have to go to successively hotter plasmas, which means that the efficiency of the whole process tends to decrease. The spectra, as I mentioned, are very complex. This is the spectrum of tin, actually, which was analyzed by Chernoff and Ryabtsev some years ago. And in fact, the spectra are extremely complex. These are scatter plots of the 4D of these transitions going from n equals 9 down to n equals 1 in platinum. And each dot here, the blue dots basically represent one transition. The red ones are 100 transitions binned in a 0.01 nanometer interval. And only the very intense lines at the top get out. There's a further complication when you go to very high Z, that you can get these kind of transitions as well, 4D to 4F, in the presence of an open 4F shell. And there, the spectra are extremely complex. And the net result is that you only tend to see strong lines from 3 isoelectronic sequences, okay, from essentially closed shell or single electron outside closed shell or single electron vacancy species. The other problem I mentioned is opacity, and the way you can control what determines the opacity essentially is the plasma density. So, for example, if you take a plasma of a spectrum of pure lanthanum, it looks like this. If you use 1% lanthanum, it looks more like this. The reason being that the strongest transitions get absorbed. The emission here is from very high stages, okay, of which you don't have too many in this spectrum. And over here, you're getting a lot of the weak lines are coming through because they're not really absorbed. Okay? If you go to different pulse durations, this again, spectrum of solid xenon with a nanosecond laser, you get lots of lines appearing in absorption. Using picosecond plasmas, absorption is less of a problem because you overheat the plasma. The plasma is tiny during the duration of the laser pulse. This might be maybe 20 microns or so. After the laser switches off, the plasma expands, cools, and at that point you start getting emission from the stages you want, but at lower density. The other thing you can do is change the laser wavelength. As you decrease the wavelength, you go to higher density. So this is, say, a spectrum of gadolinium taken with a YAG laser. its second harmonic and the third harmonic. And the third harmonic, the plasma is now at about 1% of solid density, so you actually get complete self-absorption of the UTA. And again, if you just switch from a CO2 laser to a YAG laser, in the CO2 laser, the density is down by a factor of 100, so you actually get an optically thin spectrum. And this is a real optically thin spectrum taken at the LHD in NIFS in Japan. Looks quite like the CO2 spectrum. So if you want good radiation transport, use the CO2 laser. Okay, I mentioned that all these transitions tend to sit on top of one another. The main various attempts have been made to identify this contribution of individual ion stages. The fascinating thing is if you use in charge exchange spectroscopy, this is a lovely experiment performed by Hajime Tanema in TMU in Tokyo. You have along here just a single electron capture spectra, and you expect, for example, in tin 15, or which is tin 14 plus, a single resonance line, which corresponds to just the shoulder here. But you get a feature which is much bigger than that, and that feature is due to satellites. Okay? And again, there's very strong configuration interaction in the satellites. So here you've got 4p to 4d, d to f, and p to s transitions all mixing to give you a big pileup of intensity in the UTA position. If you go to using, and this is a recent result from that received by Hayato Ohashi at UEC in Tokyo, using the EBIT. Again, these are Cowan code calculations, and here we've got the emission spectra in this case, with decreasing ion stage. And these I want to analyze these things. Okay, now the other thing I mentioned is the water window. And in the water window, you've got, you can have absorption. You want to get a source that operates where you can actually look at the absorption of carbon and nitrogen, but for water is transparent. So it covers a wavelength range from 2.3 to about 3.34 to 4.38 nanometers. Okay, I won't go through much of this, but this is sort of there are two ways of approach. One is tomography, where you put a frozen sample in here, image using a zone plate onto the sample, and then collect the image using another zone plate. There's a group now in Japan who are interested in using the sort of lithography type approach of using mirrors to collect the radiation, okay, to try to get single shot imaging. Here's typical spectra in the water window. Line spectra sources are available using carbon and nitrogen already. The problem is that none of these wavelengths, strong line emission corresponds to the wavelength of an available multi-layer mirror, so you can't use collectors. However, we have the idea of maybe using either these delta n equal 1 transitions or delta n equal 0 transitions in the water window. And this has led us to do a lot of spectroscopy. Now, I'll just flash through this very quickly. These are some data taken at the LHD and NIFS, and again, we succeeded in identifying the lines from silver-like, palladium-like, and rhodium-like spectra in these ions. We've also, in Dublin, looked at the emission of these things here in black, okay? And again, here's sort of emission from the second transition row using the Cowan code is quite straightforward to identify what the origin of the different peaks. Okay, so there's a lot of spectroscopy still to be done on these things. Also, if you change the laser power, you can basically shift to shorter wavelengths. A feature that's important here is that you also get satellite contributions on the long wavelength side of each of these arrays, which tends to broaden them and actually works towards if you're trying to develop a light source. In fact, in molybdenum, we've succeeded in showing that you can actually get these UTAs to nicely match the emission the reflectance characteristics of some available multilayers. So these could be used as collectors, and because the multilayers have narrow reflectance bandwidth, you basically monochromatize the radiation so you can use it with zone plates. We've also looked at a lot of these second transition row elements, and we've looked at transitions in rhenium, which are here. Again, we've managed to identify lots in all these peaks. You might think this has all been done 20, 30, 40 years ago. Surprisingly, it hasn't. And also, we've looked most recently at platinum, where you get these delta n equal 1 arrays and delta n equal 0, 4 to 4, 4 to 5 arrays. We've classified a lot of these things. And now most recent thing, this is a very recent result, where we've tried to just fit a UTA model to these, to the emission from a spectrum of platinum to infer the ion population. Because it turns out that, okay, the ion distributions are easy to calculate for nanosecond laser-produced plasmas, not so for picoseconds. So this is basically, we're going to try in the future to extract ion populations from the shapes of these things so that we can actually benchmark a plasma model that's being developed. So just a conclusion then, and future plans. Well, what we're doing here is, okay, we want to just keep on extending this because very little spectroscopy, and this is really classical spectroscopy, but very little has been done on these very high Z materials. We also want to look at, an interesting thing from a physics point of view, is to just investigate what happens to these 4 to 5 arrays in the region of the spectrum where you've got 4F, 5S level crossing and so on. And we also want to look at, and Takashi Kashiguchi is now building a CO2 laser with a tunable duration from about 1 to 10 nanoseconds, which will give us nice optically thin spectra. So with that, then I'd just like to thank various collaborators who have helped us with this research over many years, various funding agencies, and thank you for your attention.